the James Webb Space Telescope found a planet orbiting the nearest star to Earth, then watched it vanish without a trace. No debris, no explanation, no precedent in the history of astronomy. Today, we're going inside astronomy's greatest unsolved mystery, the vanishing world of Alpha Centauri, and the question keeping every astronomer on Earth awake at night. Before we start, if you enjoy exploring the universe's greatest mysteries, a quiet subscribe helps this channel reach further. Now, let's begin. Over 5,700 exoplanets have been confirmed in the history of astronomy. 5,700 worlds orbiting distant suns catalogued, studied, documented. Some are scorching gas giants completing a full orbit in less than 3 days. Some are frozen rocks drifting at the outer edges of dying stars. Some tantalizingly sit in the zone where liquid water could pool on a surface. Scientists have found planets made primarily of diamond planets, where it rains iron planets so dark they absorb 99% of the light that touches them. In all of that catalogue, 5,700 entries and counting, not once has a confirmed planet simply vanished. Not once has a world appeared clearly in the data. We've been analyzed by a team of specialists, passed every verification test available. We've been announced to the global scientific community, and then 60 days later, ceased to exist in any observable sense, until August 2025. What disappeared was not a faint smudge at the edge of detection. What disappeared was an object estimated to be approximately 95 times the mass of Earth. To put that in terms that land differently, if every person on the planet contributed one Earth to a pile, that pile would need to be built 95 times over just to match the mass of what went missing. This was not a small rock. This was a gas giant, a colossal sphere of hydrogen and helium held together by its own gravity. The kind of object that dominates entire orbital systems, that generates its own internal heat, that can be seen glowing in infrared from light years away. Objects like that do not disappear. The laws of physics, as currently understood, provide no mechanism by which a planet nearly 100 times Earth's mass simply stops being detectable. There is no switch. There is no trapdoor in space. Mass does not evaporate. And yet, the star in question is Alpha Centauri A, the larger of the two sun-like stars in the nearest stellar system to our own sun, sitting 4.3 light-years away. In May and June of 2025, a team of astronomers used the James Webb Space Telescope to observe the region around Alpha Centauri A. After weeks of data processing, calibration, and cross-checking, a signal emerged, a faint but consistent point of infrared light at a specific location, moving in a way consistent with a planet bound gravitationally to the star. The team ran every standard verification. The signal held. In August of 2025, they announced the discovery publicly, a Saturn-mass gas giant orbiting the nearest sun-like star to Earth. The announcement generated headlines across every major outlet on the planet. The implications were staggering. Alpha Centauri A is not some anonymous star in a distant corner of the galaxy. It is our immediate neighbor, close enough that the light reaching Earth from it tonight left that star 4 years ago. A planet there is not an abstract data point. It is a potential destination. And then in October 2025, a separate team pointed the same telescope at the same star and found nothing. No infrared signal, no point of light, no trace whatsoever of the object that had been documented just 60 days earlier. The follow-up team published their non-detection with careful, measured language, noting they were not accusing the original researchers of error. They were simply reporting what the data showed, or rather, what it did not show. What followed was unlike anything the field had seen before. Every previous controversy in exoplanet science, and there have been several involved, either a single disputed claim that quietly faded, or a retraction that resolved itself within months. What the Alpha Centauri situation produced was something different. A sustained, public, unresolved scientific standoff between multiple groups of credentialed researchers. all working with the most advanced space telescope ever built, all arriving at incompatible conclusions about the same patch of sky. This is the first planet in history to generate this kind of dispute at this scale. Not because scientists disagree, disagreement is routine in science, but because the object in question, if real, is physically incapable of behaving the way the data suggests it behaved. A planet that massive cannot simply turn off. Which means either the most sensitive infrared observatory ever constructed was fooled by something with extraordinary precision, or the universe contains a phenomenon that current physics has no language to describe. And the question underneath both possibilities is the one that keeps researchers uncomfortable at 3 in the morning if the James Webb Space Telescope, a $10 billion instrument that took 3 decades to build, and represents the absolute frontier of human optical engineering, can produce results this contradictory about a single object. What else might it be getting wrong? What other signals in its catalog might be flickering at the edge of something we do not yet understand? But to understand why the disappearance itself is physically impossible, not just unlikely, not just strange, but a genuine violation of everything scientists expect from objects of this mass, it is necessary to understand what Alpha Centauri actually is, and why this star system has kept astronomers awake for decades. Picture the entire Milky Way galaxy, compressed down to the size of the continental United States. Every star, every nebula, every spiral arm, scaled proportionally to fit between the coasts. At that scale, the distance from one side of the country to the other represents 100,000 light-years. The Sun sits somewhere in the Midwest. Alpha Centauri, at 4.3 light-years away, would be positioned less than the width of a sheet of printer paper from the Sunday. Not a foot away, pardon, inch away. The width of a single sheet of paper that is what separates humanity's home star from its nearest neighbor on any honest map of the galaxy. The two systems are, by any galactic standard, essentially adjacent. This is the first thing to understand about why Alpha Centauri is not just another star on a list. It is the next door over in a neighborhood that stretches for 100,000 light-years in every direction. But Alpha Centauri is not one star. It is 3. And the structure of this triple system is worth understanding because it shapes everything about why a planet there is both plausible and extraordinarily difficult to confirm. The two primary stars, Alpha Centauri A and Alpha Centauri B, orbit each other in a gravitational partnership that takes approximately 80 years to complete one full cycle. Think of them as two adults in the same household, circling a shared center of gravity. At their closest approach, they are separated by a distance roughly 11 times that between Earth and the Sunday. At their farthest, that gap stretches to about 36 times that distance. In terms of the solar system, they range from slightly beyond Saturn's orbit to well beyond Neptune's, always close enough to influence each other's gravitational environment, never far enough apart to be truly independent. Then there is the third member of the system, Proxima Centauri. Proxima orbits the AB pair at a distance approximately 13,000 times the Earth-Sun distance. That is so remote that Proxima takes an estimated 500,000 years to complete a single orbit around its two companions. In practical terms, Proxima behaves like a separate star, but gravitationally, it remains tethered across that enormous gulf part of the same family, despite living what would be in human terms in a different city entirely. If Alpha Centauri A and B are the father and mother of the household, Proxima Centauri is the adopted child, living 1,000 miles away, still connected, still sharing a last name on the gravitational family tree, but operating in its own world. Now here is the detail that most casual coverage of Alpha Centauri gets wrong. When people discuss this system, they often focus on Proxima, because Proxima is technically the single closest star to the Sunday. And in 2016, that focus intensified when astronomers confirmed the existence of Proxima Centauri B, a planet roughly Earth mass orbiting within Proxima's habitable zone. The announcement was celebrated as a landmark. The nearest star to the Sun had a planet in the right zone. But Proxima Centauri is a red dwarf. It is smaller, dimmer, and cooler than the Sun by a substantial margin. More critically, red dwarfs are violently active. They produce intense stellar flares on a regular basis, blasting nearby planets with radiation that over geological time can strip away atmospheres entirely. The habitable zone around a red dwarf sits so close to the star that any planet there is almost certainly tidally locked one hemisphere in permanent daylight, the other in permanent frozen darkness. Proxima b, even in optimistic models, is not an environment that resembles anything hospitable by the standards life on Earth requires. Alpha Centauri A is a fundamentally different situation. Alpha Centauri A is classified as a G-type star, the same category as the Sunday. Its mass is approximately 10% greater. Its surface temperature is nearly identical. The light it produces is sunlight, in any meaningful sense of the word. If a rocky planet orbited Alpha Centauri A, at roughly the same distance Earth orbits the Sun, it would receive similar warmth, similar radiation, similar conditions. The habitable zone around Alpha Centauri A is real, it is stable, and it is located at a distance where liquid water on a surface is physically plausible. This is the point that matters. Alpha Centauri A is not the closest star, but it is the closest star that looks like the Sunday, and that distinction is everything. Because every model of life, as it exists on Earth, and by extension every model of what conditions might allow life to emerge elsewhere, is built around a G-type star. Proxima is interesting. Alpha Centauri A is relevant, which leads to the detail that reframes the entire situation. Alpha Centauri A sits 4.3 light-years from Earth. Radio waves and light travel at the same speed, roughly 300,000 kilometers per second. At that speed, it takes 4.3 years for any signal to cross the gap between the two systems. Simple arithmetic then produces a quietly unsettling conclusion. Any radio transmission that left Earth in the year 2021 reached Alpha Centauri A in 2025. If there is a rocky planet in the habitable zone of Alpha Centauri A right now, and if anything on that planet were capable of receiving radio signals, it would be receiving Earth's broadcasts from 4 years ago at this very moment, not in some distant future. Now, the geometry of the situation is already that intimate. That is why this is not a story about an abstract scientific controversy over a dataset. It is a story about the nearest place in the universe where the question of other worlds is not theoretical, and about what happened when humanity finally had a tool powerful enough to begin answering it. That is the reason why, when the James Webb Space Telescope turned toward Alpha Centauri A in spring of 2025, every astronomer in the field was watching, and those results changed everything, only to take it all back. Imagine standing beside a freight truck at night, its headlights blazing at full intensity directly into your eyes. Somewhere on the body of that truck, a single firefly has landed. You cannot see it. The headlights overwhelm everything, your retinas, your peripheral vision, any chance of detecting that tiny pulse of bioluminescent light. Now, imagine trying to see that firefly, not from a few feet away, but from a distance of 4.3 light-years. That is the problem the James Webb Space Telescope was designed to solve, and the instrument it uses to solve it is called a coronagraph. In simple terms, a coronagraph is a precisely engineered mask that blocks the light from a star, the same way placing a thumb over a blinding light source allows the eyes to see what surrounds it. The mask is not crude. It is calibrated to block starlight down to a fraction of a pixel, suppressing the glare by a factor of billions, so that the faint infrared glow of an orbiting planet, a glow roughly as significant in relative terms as that firefly next to the truck's headlights, can be detected by the telescope's sensors. This is what the Webb team pointed at Alpha Centauri A, beginning in the late spring of 2025. The telescope locked onto the star with a precision that holds pointing stable to within a few thousandths of an arc-second, a unit so small that 1 arc-second is itself only 1/3600th of a single degree. The coronagraph mask was positioned over the star. The infrared cameras began accumulating data. And then the team waited not for seconds, but for weeks of repeated observation sessions, each lasting several hours, each generating gigabytes of raw data transmitted back to Earth via radio. What happened next was not a eureka moment. It never is in real science. The data arrived in a form that looks nothing like a photograph. It arrived as numerical arrays, long tables of detector readings, encoding the position and energy of individual photons. Processing those arrays into something scientifically meaningful required running them through calibration pipelines that account for detector imperfections, stray light, thermal fluctuations inside the telescope, and dozens of other instrumental effects. Each step removed noise. Each step required decisions about methodology. Each step took time. The team worked through the data the way a detective works through a crime scene, not by waiting for an obvious answer, but by systematically eliminating every alternative explanation. They rotated the telescope between exposures, a technique that allows real astronomical objects to be separated from instrumental artifacts. Artifacts rotate with the telescope, while real objects stay fixed relative to the star. They compared images taken at different infrared wavelengths to see whether any candidate signals showed the spectral properties expected from a planet. They checked their candidate detection against star catalogs and deep sky surveys, confirming that no known background object existed at that precise location. Week after week, the candidate signal survived every test. It appeared in multiple, independent images. It moved with Alpha Centauri A through space, confirming it was gravitationally associated with the star rather than a coincidental background source. Its brightness at different infrared wavelengths matched theoretical models of a warm gas giant, specifically a planet in the mass range of Saturn, still radiating heat from its formation, with atmospheric signatures consistent with methane and water vapor. One team member later recounted in an interview published after the announcement that the data review process became so consuming that he began dreaming about infrared spectral graphs, waking up at 2 a.m, mentally checking whether a particular absorption feature had been properly accounted for in the analysis. That detail, offered almost as a footnote, communicates something real about the weight of what they were looking at. These were not casual observers skimming a result. They were people who had stared at this data long enough that it had colonized their sleep. The signal reached a confidence level of 5 sigma. In physics and astronomy, sigma is a unit of statistical certainty. A 5 sigma detection means the probability that the signal is the result of random noise, a coincidental fluctuation in the data that happens to look like a planet, is less than 1 in 1 million. This is the threshold used in particle physics to declare the discovery of a new particle. It is the standard applied when announcing the detection of gravitational waves. It is the bar the scientific community has agreed represents the point at which a result is too robust to be dismissed as chance. 1 in 1 million. The team submitted their findings to a major astronomy journal in August of 2025 and simultaneously released the results publicly standard practice for significant discoveries where the scientific community benefits from immediate access even before formal peer review is complete. The announcement was precise and measured in its language, but the conclusion was clear. A gas giant approximately equal in mass to Saturn had been detected orbiting Alpha Centauri A, the nearest Sun-like star to Earth. The question that follows is the one with no clean answer. If the detection was statistically robust to 1 part in 1 million, if it survived every instrumental check, every cross-referencing test, every independent analysis, the team could devise. Why did it disappear? The answer does not lie in the first team being wrong. It lies in something far stranger. The second team that observed Alpha Centauri A in October of 2025 was not looking for a mistake. This point matters more than it might initially seem. They were not a group of skeptics assigned to audit a suspicious result. They were not rivals hoping to disprove a competitor's claim. They were astronomers who accepted the August announcement as a credible, well-documented detection and wanted to do what scientists do with credible detections: build on them. Their goal was to observe the planet at a different point in its orbit, to refine the measurement of its position, to gather additional spectral data to begin the process of characterizing a world that everyone in the field had already accepted as real. Nobody on that team boarded their observation run, braced for what was about to happen. Imagine photographing a building. You capture it clearly: the structure, the windows, the details of the facade, all sharp and unambiguous in the frame. 2 months later, you return to photograph it again from the same position. The street is exactly as you left it. The surrounding buildings are unchanged. The pavement is intact. No scaffolding, no rubble, no demolition equipment, no trace of any process that could explain what you are seeing, or rather, what you are not seeing. The building is simply gone. Not collapsed, not removed, not obscured. Gone as though it had never been there, while everything around it remains perfectly undisturbed. That is what the October data showed. Where the infrared signal had been, the specific coordinates, the specific wavelengths, the precise location that had produced a 5 sigma detection just 60 days earlier, there was nothing. No point source. No faint residual signal hovering near the detection limit. Nothing at all. The region of sky around Alpha Centauri A appeared as clean as if the first observation had never happened. The second team published their non-detection in November of 2025, with language that was deliberate and careful. They stated explicitly that they were not accusing the original researchers of error. They were reporting what the data showed. The absence of a signal documented with the same rigor as its original presence is itself a scientific result, and they treated it as one. What followed inside the scientific community was not panic. Panic would have been, in a strange way, easier to process. What settled over the field instead was something colder and more unsettling: controlled bewilderment. The kind of confusion that does not express itself in raised voices, but in very long silences at the ends of conversations in emails that take 3 days to arrive because the sender kept deleting drafts. In conference presentations where the speaker pauses mid-sentence because they have just heard themselves say something that should not be possible. 3 initial explanations emerged almost immediately, circulating in forums, preprint discussions, and informal communications between research groups. And all 3 had what could be called a fatal logic problem, not a small crack, but a structural flaw that made each one collapse under scrutiny. The first explanation: instrumental artifact. Perhaps the original signal was never a planet. Perhaps it was a glitch in the telescope's systems that mimicked a planetary detection and simply did not appear in the follow-up because such glitches are inconsistent by nature. The problem this requires explaining why a glitch would pass every verification test designed specifically to catch glitches, would appear at consistent positions across multiple independent images taken at different telescope orientations, and would display spectral properties indistinguishable from a real planetary atmosphere. Artifacts that sophisticated do not exist in the documented failure modes of the instrument. The second explanation: the planet moved behind the star, a phenomenon called occultation, where the planet passes to the far side of its parent star from Earth's perspective and becomes invisible in the star's glare. The problem: the mathematics of orbital mechanics applied to a planet at the observed separation from Alpha Centauri A gives an estimated orbital period of 3 to 4 years. In 60 days, a planet on that orbit completes only a small fraction of its path, far too little to move from a clearly detectable position to directly behind the star, unless the orbit was aligned at an extraordinarily precise and improbable angle relative to Earth. The third explanation: the planet was destroyed in a collision with another large body in the system. The problem: a collision capable of obliterating a Saturn-mass object does not leave a clean sky. It leaves a debris field, a glowing, expanding cloud of superheated gas and fragmented material radiating intensely in the exact infrared wavelengths Webb observes. That debris would be visible for years. The October follow-up showed no such cloud. Alpha Centauri A sat in the data looking exactly as it always had. A quiet, middle-aged star, utterly unremarkable. All three explanations demanded coincidences, stacked on coincidences, or required the absence of physical evidence that the laws of thermodynamics and momentum say should exist. None of them held, but this was not the strangest part. The strangest part came when they looked a third time and saw something flickering like a candle in the wind. In December of 2025, multiple teams were granted James Webb Space Telescope observation time to look at Alpha Centauri A. The scientific community had reached a point where the only responsible path forward was to accumulate more data, different instruments, different infrared wavelengths, different coronagraph configurations, different teams analyzing independently. The goal was clarity. What they got instead was something that made the original disappearance look, by comparison, almost straightforward. The December observations began producing results that nobody had prepared a framework to interpret. During one observation session, a faint point of infrared light appeared near the expected position of the planet, not as bright as the original August detection, but present, measurable, real enough to register above background noise. The team noted it carefully, tagged the coordinates, logged the brightness at each wavelength. A few hours later, during the same observing run, the same region of sky was imaged again as part of the standard rotation protocol designed to separate real sources from instrumental artifacts. The signal was gone, not dimmer, not shifted slightly in position, gone as completely absent as it had been in the October non-detection. And then, in a third image, taken later, that same night, something appeared again, at approximately the same location, at roughly 30% of the brightness recorded in the original August announcement. The January 2026 observations confirmed that this was not a data reduction error or a calibration anomaly isolated to a single session. Across multiple independent observation runs, separated by days and sometimes weeks, the behavior repeated. A signal present in one image, absent in the next, then partially present again, then gone, then back at an entirely different intensity level, with no discernible cycle, no predictable timing, no pattern that any existing model of planetary physics could generate. One observation documented a source at approximately 30% of the August brightness. 3 days later, a different team's observation found nothing with their detection threshold low enough to rule out anything brighter than 10% of the original signal. 1 week after that, a third observation recorded a faint source again, but at a position slightly offset from where the calculations placed the planet's orbital motion, not by much, but enough to introduce additional uncertainty about whether all these flickering signals were even coming from the same object. The most accurate comparison available from everyday experience is a Wi-Fi connection in a building with an old router. Sometimes the signal reads at 80% strength and the connection is stable. 20 minutes later, it drops to 30% for no apparent reason. An hour after that, the connection disappears entirely. Even though the router is functioning normally, the modem shows no errors and the internet service itself is uninterrupted. Then it comes back unprompted, at 60%. The infrastructure, the router, the cables, the provider is fine, but the signal behaves as though it exists in a state of constant, sourceless instability. Apply that image to an object 95 times the mass of Earth, orbiting a stable middle-aged star, and the dissonance becomes apparent immediately. Wi-Fi fluctuates because radio signals interact with physical environments, walls, interference from other devices, atmospheric conditions inside a building. Those are chaotic systems with dozens of variables. But a gas giant planet in open space orbits its star in a gravitational environment that is, by astronomical standards, extraordinarily clean. There are no walls. There is no interference in the radio frequency sense. The physics governing how such an object emits infrared radiation is well understood. Temperature determines emission. atmospheric composition shapes. The spectral signature rotation introduces slow and predictable variation. None of those mechanisms produce flickering on a timescale of hours. Not by factors of 3 or more, not randomly, not without leaving some physical signature in the data that would point toward an explanation. This is the precise reason why the flickering is more disturbing to researchers than a clean disappearance would have been. A complete disappearance, a planet present in August and simply absent in October, is a problem with a defined shape. It is bounded. Scientists can list the possible explanations, evaluate each one against the evidence, and even if none of them fully work, at least the problem is contained. There is a before and an after. Something changed once, and the task is to figure out what. But flickering has no defined shape. It is a behavior that exists outside the boundaries of known planetary physics, which means it cannot be evaluated against existing models because no existing model predicts it. A planet cannot be selectively undetectable for hours and then detectable again. A gas giant cannot vary its infrared output by a factor of 3 or more over a period of days without a physical mechanism driving that variation. And no known mechanism for objects of this type operates on those timescales with that degree of irregularity. Variable stars exist, and some vary dramatically, but their variability follows patterns. Cepheid variables pulsate with clockwork regularity. Eclipsing binaries dim on schedules determined by orbital geometry. Even the most chaotic stellar variables, like certain categories of eruptive stars, show statistical patterns across their outbursts. The Alpha Centauri flickering showed none of these patterns. Different teams analyzing the same datasets reached genuinely different conclusions about whether the signals they were seeing were real detections or noise, which itself indicates that the signals were hovering in a regime where the public distinction between detection and non-detection was becoming philosophically ambiguous. By February of 2026, the astronomy community was not just confused about Alpha Centauri A. It was confronting a more uncomfortable possibility that the events of the previous 6 months had exposed a gap in the conceptual vocabulary of planetary science. Not a gap in technology, the telescope was working. Not a gap in data, there was plenty of it. A gap in the theoretical framework. A behavior that the existing literature had no category for. And here is the question that follows naturally from that gap. The one that researchers were asking each other in the margins of preprint papers and the hallways of conferences in early 2026. If an object 95 times the mass of Earth can flicker in and out of detectability in ways that no current physical model predicts, what does that say about everything else in the exoplanet catalogue that has been observed only briefly at intervals of months or years and declared understood? Every confirmed exoplanet in existence has been observed in a limited number of snapshots. Even the most studied ones have been seen only at the resolution that current technology permits. The assumption underlying the entire field is that planets are stable, predictable objects, that an observation taken today and an observation taken 6 months from now will tell a consistent story about the same object. Alpha Centauri A's data does not support that assumption. Not for this object. In this period, under these observing conditions. That does not mean the assumption is wrong for all other planets, but it introduces a question that was not seriously on the table before August 2025. What if some fraction of the catalogue contains objects that are more dynamically complex than the models assume, and we simply lack the temporal coverage to see it? 4 hypotheses have emerged from the scientific community's attempt to contain this problem, and each one examined in order is stranger and more consequential than the last. The first involves the limits of the instrument itself, and what it means when the most sophisticated optical engineering in human history produces incompatible results. The second involves the space between planets, the dust debris, and structure of stellar systems in ways that current surveys may be systematically underestimating. The third reaches into the history of the solar system for evidence of catastrophes that leave no clean signature. And the fourth arrives at a possibility that sits at the boundary between planetary science and something genuinely new. A behavior in gas giant atmospheres that, if confirmed, would require rewriting portions of the models used to interpret every infrared observation of every distant world. None of them are comfortable. All of them are serious. And the order in which they fall apart is itself a kind of story about what science looks like when it reaches the edge of its current map. The instinct, when a $10 billion telescope produces a result that later cannot be reproduced, is to conclude that the telescope made a mistake. That instinct is understandable. It is also, in this case, too simple, and getting it wrong matters because the real situation is considerably more unsettling than a hardware failure. The James Webb Space Telescope did not malfunction. Its detectors performed within expected parameters. Its coronagraph aligned correctly. Its data transmission was clean. Every system health check conducted during and after the August 2025 observations returned normal readings. When engineers reviewed the instrument logs for any anomaly that could explain a false detection, they found nothing that would account for a signal of that consistency, that brightness at that specific location, surviving that many independent verification checks. So the question reframes itself. It is not, did the telescope make a mistake? It is, can the physical reality of observing an object across 4.3 light-years of space create an illusion so perfect, so internally consistent, so precisely calibrated to resemble a real planet, that even the most rigorous verification protocols available to modern astronomy cannot distinguish it from the genuine article? The answer, uncomfortably, is yes. Under specific circumstances, it can. Consider what happens when a driver looks through a windshield that has been scratched by years of use and road debris. At night, oncoming headlights pass through those scratches and scatter. The brain, which processes visual information by constructing the most plausible interpretation of the signals it receives, does not present the scratches as scratches. It presents them as additional light sources. A single headlight appears to become three, arranged in a pattern that looks entirely convincing, until the driver consciously reminds themselves that only one car is actually approaching. The illusion is not a failure of the eye. The eye is functioning perfectly. It is a failure of interpretation in a system, processing imperfect data, and crucially, the person experiencing the illusion has no internal signal that anything is wrong. The three lights feel as real as the one. Astronomical instruments are not human eyes, but they face an analogous challenge at the limits of their sensitivity. The James Webb Space Telescope observes Alpha Centauri A across 4.3 light-years, using a coronagraph that suppresses starlight by a factor of billions, but not to zero. Residual starlight always leaks past the mask. That residual light interacts with the telescope's optical surfaces, the edges of the coronagraph mask, the structure of the detector array, and the thermal environment of the instrument housing. These interactions can produce what are called speckles, quasi-random patterns of constructive and destructive interference in the residual starlight, that in infrared images can appear as faint point sources at fixed positions relative to the star. Speckles are the scratched windshield of space telescope imagery. They are artifacts of the observing physics, not failures of the hardware. And the most dangerous characteristic of a speckle is that it can mimic a planet almost completely. It appears at a fixed position relative to the star. It has a consistent brightness across multiple exposures taken at the same telescope orientation. It can even, depending on the specific optical path that generates it, they produce an apparent spectral signature, a pattern of brightness at different wavelengths that resembles the infrared emission of a warm gas giant. The standard technique for separating speckles from real planets is the telescope rotation method. Take images at multiple different orientations and compare them. Real planets stay fixed relative to the star as the telescope rotates. Speckles generated by the telescope's own optics rotate with the instrument. The August 2025 team applied this method. The signal they reported did not rotate, it stayed fixed relative to Alpha Centauri A as a real bound companion would. But here, is where the statistics become treacherous. A 5 sigma detection is often described correctly as a result where the probability of the signal arising from pure random noise is less than 1 in 1 million. That sounds definitive. In isolation, it nearly is. But the James Webb Space Telescope does not observe one patch of sky containing one candidate signal. It processes millions of data points across thousands of observation programs. When any system generates that volume of measurements, the mathematics of probability guarantees that some fraction of those measurements will produce apparent detections that pass statistical thresholds through coincidence rather than reality. A 1 in a million chance, encountered across millions of independent tests, is no longer rare, it is expected. This is not a theoretical concern, it is the documented history of astronomy. In the 19th century, the French mathematician Urbain Le Verrier, the same man who correctly predicted the position of Neptune from gravitational perturbations in Uranus's orbit, became convinced that irregularities in Mercury's orbital path could only be explained by an undiscovered planet orbiting between Mercury and the Sunday. He named it Vulcan. Subsequent observers, including several with excellent reputations and high-quality instruments for their era, reported seeing it. A transiting object crossing the face of the Sun was documented on multiple occasions by independent witnesses. Orbital calculations were published. Vulcan was mapped, theorized, discussed in the leading journals of the day as an established member of the solar system. It did not exist. Every observation was a misidentification. Sunspots, background stars, instrumental artifacts processed by human visual systems, and confirmation-biased analytical frameworks that had already decided what they were looking for. The planet that a generation of astronomers saw was a collective illusion constructed from real data misinterpreted. The astronomy community, following the Alpha Centauri situation, was aware of this history. The online response reflected it with a precision that was almost comforting in its humor. The astronomy community on Reddit, where researchers and enthusiasts had been tracking the story with intense interest since August, produced a meme that circulated widely through December 2025 and into early 2026, a diagram labeled Schrödinger's Planet, with the caption indicating that the object simultaneously existed and did not exist depending on the moment of observation. The joke landed because it was not entirely a joke. It captured something real about the epistemic state of the situation, a detection that was undeniable in one dataset and absent in the next, with no clean way to determine which represented reality. But the false positive hypothesis, satisfying as it might be in its simplicity, runs into a wall when confronted with the December and January flickering data. A speckle or instrumental artifact behaves consistently. If a particular optical path in the telescope generates a false signal at a specific position, that signal appears every time the telescope is configured the same way. Not randomly, not intermittently, not at varying intensities across. Different observation sessions conducted by different teams using different instrument settings. A false positive that appears at 30% brightness one day disappears entirely 3 days later, and reappears at a slightly different position 1 week after that, is not behaving like any known category of instrumental artifact. It is behaving like something that is actually there but unstable, which is a different problem entirely. The false positive hypothesis cannot explain the flickering, which means the instrument was not simply deceived by its own optics, which means something at that location, something real and physical, is doing something that no current model of planetary behavior predicts. The hypothesis of instrumental error cannot explain the flickering, which means there is a darker possibility that something was physically blocking it. Space is not empty. This statement runs against the intuition that most people carry about the universe. The word space itself implies absence, a void between objects, a vacuum through which light and planets and spacecraft travel without obstruction. And in the broadest sense, space is extraordinarily empty by any standard that applies to ordinary human experience. The density of material between stars is so low that the best vacuum chambers ever constructed on Earth, evacuated to the furthest limits of current engineering, are denser than the interstellar medium by several orders of magnitude. But extraordinarily empty is not the same as nothing. And within individual stellar systems within the gravitational domain of a single star, the concentration of material rises sharply. Planets form from disks of gas and dust. After the main planets coalesce, vast quantities of residual debris remain: boulders, pebbles, dust, grains, ice particles, the shattered remains of objects that never grew large enough to become worlds. This material does not vanish. It persists, orbiting the star in structures that range from the dense, visible rings of Saturn to the diffuse, nearly invisible zodiacal dust that fills the inner solar system and produces a faint glow along the ecliptic, visible from Earth on dark, moonless nights. Think of driving on a long highway through fog that is not uniformly distributed. For several miles, the road is clear, visibility excellent, every detail of the landscape crisp and readable. Then, without warning, a dense patch of fog closes in visibility, drops to near zero. The road ahead disappears, and the driver navigates by instinct and lane markings alone. A mile further, the fog lifts again to near perfect clarity. The car has not changed speed. The road has not changed. The fog is simply structured in a way that creates dramatically different visibility conditions at different points along the same path. A planet orbiting through a debris disk experiences something structurally similar. The debris is not uniformly distributed around the orbit. It concentrates in certain regions, resonance zones maintained by gravitational interactions, collision families generated when larger objects break apart, asymmetric clumps produced by the gravitational influence of other planets in the program's system. A planet moving through a particularly dense clump of this material could, in principle, have its infrared emission partially or completely attenuated the dust, absorbing and scattering the planet's outgoing heat radiation before it reaches a telescope 4.3 light-years away. For Alpha Centauri A specifically, the evidence regarding debris structure is indirect but not negligible. Infrared observations of the system, accumulated over several decades, show faint excess emission at certain wavelengths, a signature that in other stellar systems has been interpreted as thermal radiation from warm dust. The signal in Alpha Centauri A's data is subtle enough that its significance has been debated, but subtle does not mean absent. According to preliminary analyses of accumulated infrared data, the system may harbor dust structures that have not been fully mapped, concentrations of particulate material orbiting the star in configurations that current surveys lack the primed resolution to characterize completely. This makes the debris obscuration hypothesis genuinely worth examining. If Alpha Centauri A has a debris disk, even a sparse one, and if the purported planet's orbit passes through a region of elevated dust density, then the planet's infrared signal could be diminished or suppressed during those passages. The planet would not disappear. It would simply be hidden behind a curtain of its own system's material, invisible to Webb's cameras but physically intact, continuing its orbit through the obscuring region until it emerged on the other side. The hypothesis is attractive for a specific reason. It requires no new physics. Debris disks exist. Dust obscuration of stellar objects is documented. The mechanism is real and understood. If the numbers work, it provides an explanation that fits within the existing framework of planetary science without requiring any revision to fundamental models. But the numbers present a serious problem. Dust in a debris disk orbits the central star at speeds determined by the disk's radial position, typically tens of kilometers per second, for material in the inner few astronomical units of a mature stellar system. At those speeds, individual dust grains complete full orbits in years, and the large-scale structure of the disk evolves on timescales of thousands to millions of years. Dense clumps within the disk do exist and do move. but their movement relative to a planet passing through them is gradual. A planet transiting through a dense region of the disk would experience a slow, predictable change in brightness, a dimming that developed over weeks or months, not a disappearance that occurred over days and reversed itself erratically over hours. The flickering data from December 2025 and January 2026 showed brightness changes occurring on timescales of hours to days. Debris disk material does not reorganize itself that quickly. A curtain of dust that closed in hours would require particle densities and relative velocities that are physically inconsistent with the stable orbital mechanics of a mature stellar system approximately 5 billion years old. The obscuration that could hide a planet in the morning's observation and reveal it again in the evening's observation would need to be moving through the planet's vicinity at extraordinary speed, fast enough that ordinary debris disk dynamics cannot account for it. Unless it is not ordinary debris disk material at all. Unless the dust generating this flickering is not ancient, settled material left over from the system's formation, but something freshly produced. Something generated recently, perhaps catastrophically, in an event that released a concentrated cloud of particulate matter into a specific region of the Alpha Centauri A system. Something that is still dispersing, still evolving, still dense enough in places to block the planet's emission and thin enough in others to let it through, and doing so on timescales that reflect the dynamics of a fresh, expanding debris field rather than a stable, aged disk. If that is the case, if the dust is not ancient but new, then the question changes completely. It stops being a question about the planet's visibility and becomes a question about what catastrophic event created the dust in the first place. And that is when the story moves into genuinely frightening territory, the possibility that a cosmic catastrophe occurred right in front of us. What if the planet genuinely existed in May of 2025, but by October it was no longer a planet? This is not a metaphorical question. It is the literal third hypothesis that the astronomical community placed on the table when the first two explanations failed to hold. And it deserves to be examined seriously, not because the evidence supports it. It does not. And that absence of evidence is itself one of the most important data points in this entire story. But because the process of eliminating it reveals something fundamental about how catastrophic events in space actually work, and why the universe cannot hide them the way a mystery novel hides its killer. Planetary collisions happen. The solar system's own history confirms this without ambiguity. The leading model for the Moon's formation holds that approximately 4.5 billion years ago, a body, roughly the size of Mars, struck the early Earth at an oblique angle, excavating an enormous quantity of mantle material that was ejected into orbit and subsequently coalesced into the Moon. The evidence for this event is embedded in the isotopic composition of lunar rocks. The dynamics of the Earth-Moon system and the Moon's relative lack of volatile elements compared to Earth. It was not a gentle event. It was a collision between two rocky bodies of planetary scale, releasing energy that temporarily liquefied the surfaces of both objects and generated a debris field visible across the inner solar system for potentially millions of years. Afterward, that happened in a young, chaotic solar system, still in the process of sorting itself out. A period when planetary orbits were unstable, migration was ongoing, and the gravitational interactions between forming worlds created conditions where close approaches and catastrophic encounters were, by the standards of mature stellar systems, relatively routine. Alpha Centauri A is not a young system. Current estimates place its age at somewhere between 4.8 and 6 billion years, comparable to or slightly older than the Sunday. A system that old has had billions of years to reach gravitational equilibrium. The planets that survived that long did so precisely because they found stable orbits where catastrophic encounters with other major bodies became vanishingly rare. The dynamical sorting that produces planetary collisions happens early. By the time a system reaches middle age, the survivors have claimed their orbital territories, and the probability of one large world striking another drops to levels that strain the definition of unlikely. According to dynamical models of mature planetary systems, the probability of a collision between two bodies of planetary mass occurring in any specific month-long window is lower than the probability of winning the Powerball lottery. 3 consecutive times with 3 separate tickets. Each individual Powerball draw has odds of approximately 1 in 292 million. 3 consecutive wins would represent a probability so small that writing it out in standard notation requires moving the decimal point more than 25 places to the left. The planetary collision probability in a mature system is in that same territory, not 0 because nothing in probability is 0, but effectively 0 for any practical purpose involving human timescales. So the collision hypothesis was already improbable before a single piece of physical evidence was examined. But probability alone does not eliminate a scientific hypothesis. Evidence does. And the evidence against a planetary collision between May and October of 2025 inches, the Alpha Centauri A system, is not merely suggestive, it is decisive. When two objects of planetary mass collide, the collision does not produce a clean result. It does not cause one object to simply cease to exist while the other continues undisturbed. The physics of high-velocity impacts between bodies of that mass involve the conversion of kinetic energy into heat at a scale that defies ordinary intuition. A collision between a Saturn-mass gas giant and any impactor large enough to destroy it would release energy equivalent to billions of nuclear warheads, detonating simultaneously, not in a sequence, but in a single event, compressing the collision zone to temperatures that cause hydrogen and helium to behave in ways normally associated with the interiors of stars. The aftermath of such an event is not subtle. The debris superheated gas fragmented material from any rocky cores involved plasma expanding outward from the impact zone would form a glowing cloud radiating intensely across multiple wavelengths. In the infrared spectrum where Webb operates, this debris field would be among the brightest sources in the entire Alpha Centauri system, far outshining any single planet. The cooling process for such a cloud takes not days or weeks, but years to decades, depending on the total mass involved and the initial temperature of the collision. The debris does not simply dissipate. It expands, cools gradually, and remains detectable as an infrared excess around the star for a time frame that would encompass multiple subsequent observation campaigns. Think of a chemical plant explosion, not a contained, controlled detonation, but a catastrophic failure of a large industrial facility with multiple storage tanks, pressurized systems, and reactive materials. The explosion itself lasts seconds, but the aftermath is impossible to conceal. The heat signature persists for hours. The smoke column is visible for miles. The structural debris scatters across the surrounding area. The environmental contamination remains measurable for years. Investigators arriving at the site a month later do not find a clean, empty lot with no indication that anything occurred. They find a landscape that announces its own history in every physical detail. A planetary-scale collision is that explosion scaled up by a factor that makes the chemical plant comparison almost insultingly inadequate. And the October 2025 observations of Alpha Centauri A showed none of it. The star sat in the infrared data exactly as it always had. No excess emission at any wavelength, no expanding debris cloud, no elevated dust temperature in the surrounding space, no asymmetry in the infrared brightness profile around the star that would indicate recently ejected material. Alpha Centauri A looked to every instrument that examined it like a quiet, middle-aged star having an uneventful day, which is precisely what it looked like before the planet was ever detected, and precisely what it looked like in every subsequent observation, regardless of whether the flickering signal appeared or not. The absence of a debris signature is not merely a negative result. In science, the absence of an expected consequence, when the detection threshold is well below what that consequence should have produced, functions as positive evidence against the hypothesis that would have produced it. Webb's sensitivity in the infrared wavelengths relevant to collision debris is high enough that a planetary-scale impact occurring between May and October of 2025 would have left a signal detectable not just in subsequent observations but potentially in archived data from earlier observation programs targeting the same star. No such signal has been identified in any dataset. This evidence taken together does not merely make the collision hypothesis improbable. It eliminates it as a physical possibility consistent with the available observations. If a planetary collision had occurred in that time frame, the aftermath would be there, measurable and unmistakable in every subsequent image of the system. It is not there. Therefore, the collision did not happen. And that elimination matters beyond the specific question of Alpha Centauri A, because it closes off an entire category of explanations. Any hypothesis that requires the planet to have been physically destroyed, collision, tidal disruption, ejection from the system following a gravitational encounter, predicts consequences that should be observable. None of those consequences appear in the data. The entire destruction family of hypotheses collapses together. So, if the planet was not destroyed, not obscured by dust, and not a phantom of instrumental error, what remains is a single possibility, strange and without precedent. There is a profound difference between watching someone every day of their life and seeing 3 photographs of them taken at random intervals spanning several decades. From daily observation patterns become visible. The gradual changes in posture, in weight, in the way they carry themselves through different seasons and different years. All of it legible because the continuous record allows context to accumulate. Remove that continuity and replace it with 3 snapshots, and the same person becomes a mystery. The first photograph shows them laughing at a summer barbecue. The second, taken 19 years later, shows them sitting alone in a dim room. The third, 6 years after that, shows them running a marathon. Without the connecting tissue of daily observation, no coherent narrative emerges. Each image contradicts the expectations set by the previous one, and any attempt to construct a story from 3 data points separated by years produces conclusions that are almost certainly wrong. This is the epistemological situation that exoplanet science exists in, and it is the lens through which the 4th and most consequential hypothesis about the Alpha Centauri planet must be understood. Every planet in the solar system has been observed continuously, or nearly so, for decades. Telescopes on Earth and in orbit have tracked Jupiter, Saturn, Uranus, and Neptune through seasonal cycles, storm systems, atmospheric reorganizations, and slow evolutionary changes in their cloud structures. When Neptune's great dark spot, a storm system larger than the entire surface area of Earth, appeared in Voyager 2, imagery in 1989, and subsequently vanished entirely by the time the Hubble Space Telescope observed the planet. In 1994, scientists did not panic. They had enough contextual data about Neptunian atmospheric dynamics to understand that such storms can dissipate on timescales of years, and they had continuous monitoring data to track the transition. The disappearance of the Great Dark Spot was striking, but it was interpretable because the observational record surrounding it was dense enough to provide context. A gas giant orbiting Alpha Centauri A at 4.3 light-years of distance is not monitored continuously. It cannot be. Each observation campaign represents a brief window, hours to days of telescope time, separated from the next campaign by months. The planet exists in the observational record as a small number of disconnected snapshots with no connecting tissue between them. Whatever happens to that planet between observations is invisible. Its atmospheric state when the telescope is pointed at it is not necessarily related to its atmospheric state during any previous or subsequent observation, because an enormous amount of time during which the planet's dynamics continued evolving unobserved separates each data point. This is not a limitation that better technology alone can fix. It is a structural feature of the observational geometry. With that context established, the 4th hypothesis proposes the following. The planet detected in August 2025 is real, is still orbiting Alpha Centauri A, and has not been destroyed or obscured by external material. What changed between the initial detection and the subsequent observations is the planet's atmosphere, specifically the atmospheric state that determines how much infrared radiation reaches a telescope 4.3 light-years away. And the flickering data from December 2025 and January 2026 suggests that this atmospheric state is not merely changing, but cycling through conditions of dramatically different infrared transparency on timescales that have no documented precedent in solar system planetary science. Neptune's Great Dark Spot provides the closest available analogy, but it is an imperfect one. That storm appeared in one hemisphere and disappeared over approximately 5 years, a dramatic change by the standards of planetary atmospheres, but a gradual one by the standards of the Alpha Centauri flickering data. If the Alpha Centauri planet experienced an atmospheric event of similar character but 10 times more extreme in its effect on infrared emission, a reorganization of its upper atmosphere so comprehensive that the effective radiating temperature visible to an external observer changed by hundreds of degrees. The theoretical models of planetary atmospheric physics suggest this could reduce the planet's infrared brightness by 70 to 80%. 70 to 80% brightness reduction would move a 5 sigma detection to near or below the detection threshold of current instrumentation. The planet would not appear to disappear because it had gone anywhere or been obscured. It would appear to disappear because its atmosphere had temporarily entered a state in which it radiated far less energy in the specific infrared bands that Webb's cameras were monitoring. This mechanism is the only one of the 4 hypotheses that requires no new physics, no coincidental timing of external events, and no instrumental failure. It requires only that gas giant atmospheric dynamics at the scale and temperature relevant to the Alpha Centauri planet are more extreme and more rapid than anything documented in the solar system, which, given that the solar system's gas giants were formed around a single G-type star with a specific history, and that the Alpha Centauri planet, formed in a different environment with different initial conditions, is not an unreasonable possibility to entertain. But the hypothesis still cannot fully account for the observed flickering on hourly timescales. No known atmospheric mechanism on a gas giant, not storm formation, not cloud layer reorganization, not changes in upper atmospheric haze density, operates fast enough to produce signal variations of a factor of 3 or more within a single observation session lasting a few hours. The thermal inertia of a planetary atmosphere prevents changes that rapid. Energy redistributes through an atmosphere gradually, not instantaneously. A planet cannot meaningfully change its infrared output on a per-hour basis without a physical driver that no current atmospheric model for gas giants includes. Which means that even the most physically plausible of the 4 hypotheses, the one that requires no catastrophe, no illusion, no cosmic curtain, still leaves an unexplained residual. It can account for the disappearance in October. It cannot account for the erratic hourly variation in December and January. Those 2 behaviors may require different explanations, or they may require a single explanation that does not yet exist in the literature. This is not the failure of science. It is the exact shape that science takes when it arrives at the boundary of its current map, the place where the known territory ends and the unknown begins, marked not by a wall, but by a set of observations that the existing framework cannot process. Every major expansion of scientific understanding in history began at a boundary like this one, with data that refused to fit any available explanation and demanded that the explanation be rebuilt from a different foundation. And at that boundary there is a question larger than the planet itself waiting to be answered. Most people carry a mental image of science as a library, a large, well-organized collection of confirmed facts arranged on shelves growing steadily, as new discoveries are added and outdated entries are removed. In this image, the work of science is essentially curatorial, finding new facts, verifying them, and placing them in their appropriate location in the catalogue. The library is always expanding, always becoming more complete, always moving toward a finished state that represents total knowledge. This image is not wrong exactly. It describes something real about how scientific knowledge accumulates over time. But it misses the part that actually matters, the part where science is genuinely alive, where the outcome is uncertain, where the people involved do not know how the story ends. That part does not happen inside the library. It happens at the edge of the building, in the unlit space just beyond the last row of shelves, where the catalogue territory ends and the unknown begins. The Alpha Centauri planet exists entirely in that unlit space. And understanding what science looks like there, what it actually does when evidence is incomplete, contradictory, and insufficient for a clean conclusion, is essential to understanding why the situation unfolding around Alpha Centauri A since August of 2025 is not a failure of the scientific process. It is the scientific process operating exactly as it is supposed to at the boundary of knowledge. Consider the structure of a criminal trial. 12 jurors are presented with evidence, physical, testimonial, circumstantial, and asked to reach a verdict. The evidence is rarely complete. Surveillance footage has gaps. Witnesses contradict each other. Physical evidence is ambiguous. The jurors cannot wait for perfect clarity, because perfect clarity may never arrive. They must evaluate what exists, weigh it against alternative interpretations, and reach the most defensible conclusion available given the current state of information. The standard is not certainty. It is reasonable certainty, a threshold high enough to justify action, low enough to be achievable, with the imperfect evidence that real situations produce. Science at the frontier operates under similar constraints with one critical difference. Unlike a jury, the scientific community can return a verdict of, "We need more time." It can declare the evidence insufficient, identify what additional observations would resolve the ambiguity, and defer final judgment until those observations are completed. This is not intellectual cowardice. It is the appropriate response to a situation where premature conclusions would be worse than maintained uncertainty, where locking in a wrong answer forecloses the pursuit of the right one. The history of astronomy contains two kinds of precedent for the Alpha Centauri situation, and both are worth examining carefully because they bracket the range of possible outcomes. The first precedent is gravitational waves. Albert Einstein's general theory of relativity, published in 1916, predicted that accelerating massive objects should produce ripples in the fabric of space-time, distortions that propagate outward at the speed of light, compressing and stretching space itself as they pass. The prediction was mathematically rigorous and emerged directly from the core equations of the theory. Einstein himself, however, doubted that gravitational waves would ever be detectable. The amplitude of the distortions, even from cataclysmic events like colliding black holes, would be so vanishingly small at Earth's distance that he considered the practical detection problem essentially insurmountable. For 99 years, gravitational waves occupied exactly the kind of twilight zone that the Alpha Centauri planet currently inhabits. Theoretically well motivated, supported by indirect evidence. Pulsar timing measurements in the 1970s showed orbital decay consistent with gravitational wave emission, but never directly confirmed. The question, do gravitational waves exist as a directly detectable phenomenon, had a correct answer during all of those 99 years. But science did not have access to that answer. It existed in the unlit space beyond the shelves, real and waiting, until the Laser Interferometer Gravitational Wave Observatory detected the first direct signal in September of 2015. 99 years of possibly yes, then confirmation. The second precedent runs the other direction. For decades, beginning in the late 20th century, a significant body of indirect evidence accumulated, suggesting that a large, undiscovered planet, popularly called Planet X, later discussed under the more technical designation of a hypothetical super-Earth or ice giant in the outer solar. The system was perturbing the orbits of distant trans-Neptunian objects in ways inconsistent with the known mass distribution of the solar system. Statistical analyses of the clustering of these objects, orbital parameters, were published, scrutinized, and found by a substantial portion of the community to constitute meaningful evidence for an unseen massive body. The debate continued for years. Models were refined. Additional trans-Neptunian objects were catalogued. The evidence for the anomalous clustering was debated extensively in the literature. And then, as survey data improved and the sample of known trans-Neptunian objects grew large enough to apply more rigorous statistical methods, the apparent clustering began to dissolve. More complete data revealed that the earlier result had been a product of observational bias. The objects had been found in specific regions of sky that had been more thoroughly surveyed, and their apparent clustering was an artifact of play, where telescopes had looked not a physical signature of an unseen planet. The evidence which had looked compelling for years evaporated when better data arrived. Decades of possibly yes, then retraction. Both outcomes are live possibilities for the Alpha Centauri planet. The detection could be the first faint signal of something real. A world that better instrumentation will eventually resolve into clear, unambiguous confirmation. Or it could be a sophisticated false positive that more comprehensive data will eventually expose and eliminate. The current evidence does not distinguish between these possibilities, and anyone who claims otherwise is not reading the data honestly. A veteran astronomer with more than 4 decades of experience in observational planetary science made a remark in an informal conference discussion in early 2026 that circulated widely through the community afterward. The comment was offered without particular drama as a simple statement of professional experience. After 40 years in this field, I have learned that the universe is under no obligation to behave in ways that are convenient for our publication deadlines. The remark landed because it captured something true about the relationship between the pace of discovery and the pace of reality. The universe does not accelerate its disclosure schedule to accommodate grant cycles or career timelines. It yields its answers when sufficient effort and instrumentation are brought to bear, not before. So where does the Alpha Centauri planet sit in this history? Is it a gravitational wave waiting for its 2015 moment real theoretically supported, requiring only better technology to confirm? Or is it a Planet X, a statistical ghost, that will dissolve when the sample size grows large enough to reveal the bias hidden in the original detection? The answer will not come from reanalyzing existing data. Every available analytical technique has already been applied to the August 2025 observations and their successors. The uncertainty that remains is not computational. It is observational. More data from different instruments and different methodologies is the only path to resolution. The answer does not come from Webb alone. It comes from an observational revolution, unfolding in parallel, that could change the entire picture. On a mountaintop in the Atacama Desert of northern Chile, construction is underway on a structure that will, when completed later this decade, be the largest optical and infrared telescope ever built on Earth. Its primary mirror, not a single piece of glass, but a mosaic of 798 individual hexagonal segments working together as a single optical surface, will span 39 meters in diameter. 39 meters. A regulation NBA basketball court is 28 meters long. The mirror of the extremely large telescope is wider than the court, is long, and it gathers light across an area of approximately 978 square meters, nearly 1,000 square meters of light collecting, surface pointed at the sky. To translate that into terms that make the capability concrete, the James Webb Space Telescope, the instrument that detected, failed to redetect, and then flickered on and off over Alpha Centauri A between May 2025 and January 2026 has a primary mirror, 6.5 meters in diameter. In terms of light collecting area, the extremely large telescope outperforms Webb by a factor of roughly 36. 36 times more photons per unit time, 36 times the raw sensitivity, applied to observations where the limiting factor has consistently been signal buried just at or below the noise floor. If Webb's observations of Alpha Centauri A represent imagery taken with the finest smartphone camera available in the early years of digital photography, capable detailed by its era's standards, but constrained by fundamental physical limits of sensor size and optical resolution, then the extremely large telescope represents the professional medium-format camera used by commercial photographers working at the absolute frontier of image quality. The subject is the same. The scene is the same. The difference in what becomes visible when enough light is collected with sufficient optical precision is not incremental, it is categorical. The extremely large telescope is also a ground-based instrument, which creates a challenge that does not apply to Webb Earth's atmosphere. Light passing through the atmosphere is distorted by turbulence, the same phenomenon that makes stars appear to twinkle when viewed with the naked eye. For a telescope of this aperture, atmospheric turbulence would ordinarily smear the image to the point of destroying the angular resolution that makes the instrument valuable. The solution is adaptive optics, a system that uses laser guide stars and deformable mirrors to measure and correct atmospheric distortion thousands of times per second, restoring the image quality that the mirror's size would theoretically deliver. The extremely large telescope's adaptive optics system will be the most sophisticated ever deployed, capable of correcting turbulence with sufficient precision to achieve angular resolution that exceeds even the James Webb Space Telescope's performance for certain classes of observation. For the specific problem of detecting and characterizing planets around nearby stars, objects that are faint, sit close to a bright central star, and require both high contrast and high angular resolution to distinguish the combination of the PROSI, extremely large telescope's collecting area, and its adaptive optics correction creates capabilities that current instrumentation cannot approach. If the Alpha Centauri planet exists and is behaving as the atmospheric hypothesis predicts present, but variable in its infrared output, the extremely large telescope should be able to detect it even during periods when Webb sees nothing, because it collects enough light to pull the signal above noise, even when the planet's emission is reduced by 70 or 80%. Meanwhile, at the level of formal NASA mission planning, a separate instrument is being developed that approaches the problem from a fundamentally different architectural direction. The Habitable Worlds Observatory is currently in the early stages of concept development and scientific requirements definition. Unlike Webb, which was designed as a general-purpose infrared observatory with planet detection as one of many scientific objectives, the Habitable Worlds Observatory has a single driving scientific goal: the direct imaging and spectroscopic characterization of Earth-sized planets in the habitable zones of nearby sun-like stars. Every design choice for the Habitable Worlds Observatory flows from that objective. Its mirror will be larger than Webb's. Its coronagraph will achieve higher contrast, suppressing starlight to a greater degree and closer to the star's position on the detector than any instrument currently in orbit. Its spectroscopic capability will be optimized specifically for detecting the atmospheric signatures relevant to habitability, water vapor, oxygen, carbon dioxide, ozone, and its target list, when ranked by scientific priority, places Alpha Centauri A at or near the top, because Alpha Centauri A is the nearest sun-like star and the place where any planet in the habitable zone would appear most separated from its star as seen from Earth, making it the most favorable geometry for direct imaging of any target in the survey. If the Habitable Worlds Observatory launches as currently planned and operates as designed, it will not merely attempt to confirm or deny the existence of the Saturn-mass planet detected in August 2025. It will search the entire inner region of the Alpha Centauri A system for planets of all sizes, down to and including objects smaller than Earth, with sensitivity sufficient to detect their reflected starlight or thermal emission directly. Then there is the question of what happens if a planet is confirmed, not just suspected, but confirmed beyond reasonable doubt, with orbital parameters precisely measured and atmospheric composition partially characterized. That confirmation would immediately change the status of a mission concept that has existed at the intersection of physics, engineering, and ambition for nearly a decade. Breakthrough Starshot. Breakthrough Starshot, announced in 2016 and backed by substantial private funding, proposes to send a fleet of gram-scale spacecraft, chip-sized probes attached to thin light sails, to the Alpha Centauri system using laser propulsion from Earth, accelerated by a ground-based laser array to approximately 20% of the speed of light. These probes would reach Alpha Centauri in roughly 20 years, transmit data and imagery during a brief fly-through of the system, and return information about whatever they encountered. The concept is technically demanding at multiple levels: the laser array, the sail material, the miniaturized instruments, but none of the component technologies violate known physics. They are engineering challenges, not theoretical impossibilities. Currently, Breakthrough Starshot is a private scientific initiative, ambitious, serious, but competing with other priorities for attention and funding in a crowded landscape of space exploration proposals. The confirmed existence of a planet at Alpha Centauri, particularly a gas giant whose presence suggests the system is likely to harbor additional inner rocky worlds, transforms the mission's status. A confirmed planetary system at the nearest sun-like star is not merely a scientific target. It is a national and civilizational priority of a different order entirely. The scientific, strategic, and philosophical arguments for sending the first human-built artifact to another star system become qualitatively stronger when there is something specific, known, and mapped waiting on the other end of the prosaic journey. But all of these instruments, the extremely large telescope, the habitable worlds observatory, the eventual infrastructure of interstellar exploration, exist in future time. The extremely large telescope will not see first light until late this decade. The Habitable Worlds Observatory will not launch for many years beyond that. Breakthrough Starshot remains at the concept and development stage. None of them are available to resolve the question that has been open since October 2025. The mystery remains active. Every month that passes without resolution is a month during which the scientific community holds a conclusion in suspension, neither confirmed nor refuted, neither catalogued in the library nor removed from consideration. The planet flickered, the data conflict. The debate continues, and the telescopes that could settle it definitively are still being built. But perhaps the more important question is not whether the planet is real. It is why that question matters so much to the human species in the first place. Every event in the entirety of recorded human history, every war, every discovery, every birth and death, every civilization that rose and collapsed, every work of art ever created, every scientific breakthrough ever achieved, occurred on a powered, single planet, one world, one gravitational address. For the approximately 300,000 years that anatomically modern humans have existed, and for the several thousand years during which written records preserve the texture of human experience, the boundary of the human story has been in the most literal physical sense, the boundary of Earth. This is not a complaint. Earth is extraordinary by any reasonable measure. A geologically active, water-rich, biologically diverse world that has sustained complex life for billions of years and human civilization for millennia. But it is one world, one atmosphere that a single large asteroid impact a sufficient volcanic event or a runaway feedback in the climate system could render uninhabitable within timescales that are short by geological standards. One set of resources that is finite. One fragile membrane of air and liquid water separating the entire accumulated project of human existence from the vacuum of space. For the first time, In the 300,000-year history of the species humanity possesses, instruments capable of asking the question, "Is there somewhere else?" and receiving a scientifically meaningful answer. Not a mythological answer, not a philosophical answer. A data-driven, empirically grounded answer about specific worlds orbiting specific stars within distances that are not merely theoretical, but potentially traversable within the lifespan of a civilization. The James Webb Space Telescope represents the first generation of technology sophisticated enough to begin returning those answers for the nearest stellar systems, which is precisely why the events around Alpha Centauri A in 2025 and 2026 carry a weight that no previous exoplanet controversy has matched. But the significance of a confirmed planet at Alpha Centauri A is not primarily about that planet itself. A Saturn-mass gas giant, even one orbiting the nearest Sun-like star, is not a destination for human settlement. Gas giants have no solid surface. Their atmospheric pressures and temperatures at any accessible depth are hostile beyond remediation by any technology currently conceivable. The planet detected in August 2025, if it is real, is not where anyone is going. The significance is what it proves about the neighborhood. Alpha Centauri A is not a special star in any respect that would make it uniquely prone to planet formation. It is a middle-aged G-type star with a mass and luminosity close to the Sun's, embedded in a binary system with a history that is, by stellar standards, unremarkable. If it has a gas giant, the implication drawn from everything known about how planetary systems form is that the conditions for planet formation around nearby Sun-like stars are not exceptional. They are normal. They produce planets the same way they produce planets everywhere else in the galaxy. And if planet formation around nearby Sun-like stars is normal, then the statistical expectation is that those systems contain not just gas giants, but the full range of planetary types that planetary formation models predict, including rocky, inner worlds, at distances from their star, where liquid water on a surface is physically plausible. Think of the position Europeans occupied in the 15th century relative to the Western Atlantic Ocean. The ocean was not unknown. It had been crossed, partially explored, glimpsed from its edges. But its western boundary, what lay beyond the horizon, in the direction the winds rarely carried ships, remained genuinely uncertain. Some believed there was nothing open water extending indefinitely. Some believed there were islands. A few believed there was a continuous landmass of substantial size. Nobody had returned with definitive evidence. The uncertainty was real. But here is the crucial detail when the evidence finally arrived, when ships returned with accounts of coastlines, ecosystems, and inhabitants. The discovery was not primarily about the specific location first contacted. It was about the proof of concept. It established that the Western Atlantic was not a void, but a space containing something. That single confirmation changed the entire calculus of exploration because it answered the foundational question, is there anything there? With a yes that could not be retracted. Everything that followed the centuries of subsequent exploration, colonization, exchange, and transformation of both hemispheres flowed from that initial proof of concept. A confirmed gas giant at Alpha Centauri A functions the same way. It does not answer every question about the system. It answers the foundational one. Does this system have planets? If the answer is yes, then the framework for everything that follows further characterization. Search for rocky inner worlds. Planning of eventual probe missions is established. The question shifts from whether to explore Alpha Centauri to how. And the cascade of implications does not stop at the gas giant itself. Planetary formation models refined over decades of observation across thousands of exoplanet systems are consistent in one prediction. Gas giants rarely form alone. The disk of gas and dust that produced a Saturn-mass body also contained the material necessary for inner rocky planets smaller. Denser worlds forming closer to the star where the disk was warmer, and ice could not survive to build the massive cores that gas giants require. Jupiter analog planets in other star systems frequently occur alongside inner terrestrial worlds. The presence of one strongly suggests the presence of the other, though confirmation requires independent observation. But there is a further implication that receives less attention in public discussions of the Alpha Centauri situation, and it is one that makes the case for the planet's significance even more concrete. Gas giants have moons, not occasionally systematically. The solar system's gas giants are accompanied by extensive moon systems generated by the same disk dynamics that formed the planets themselves. Jupiter has 95 confirmed moons. Saturn has 146. The largest of these, Ganymede, Titan, Callisto, Io in Jupiter's system, Titan, Rhea, Dione in Saturn's, are not small rocks. They are worlds in their own right, with diameters measured in thousands of kilometers. With geological activity, with atmospheres in some cases, and in several cases with evidence of liquid water beneath their surfaces. Enceladus, a moon of Saturn, roughly 500 kilometers in diameter, has a subsurface ocean of liquid water confirmed by the Cassini spacecraft's direct sampling of material erupting from geysers at the moon's south pole. The ocean is in contact with a rocky seafloor, creating the hydrothermal conditions that many origin-of-life models require. Europa, a moon of Jupiter, approximately the size of Earth's moon, has a subsurface ocean estimated to contain more liquid water than all of Earth's oceans combined, kept liquid by tidal heating from Jupiter's powerful gravitational field. Neither Enceladus nor Europa is in a traditional habitable zone. Both orbit gas giants far from the Sun, receiving a fraction of the solar energy that Earth receives. Their liquid water exists not because of stellar warmth, but because of the gravitational energy their host planets continuously inject into their interiors through tidal flexing. The energy source is mechanical, not radiative, and it is independent of the star's luminosity. A Saturn-mass gas giant orbiting Alpha Centauri A would, according to the same physics that governs Saturn's moon system, almost certainly host a collection of moons. The largest of these moons could be geologically active, their interiors continuously stressed by the tidal forces of the gas giant they orbit, generating internal heat that could sustain liquid water beneath icy surfaces, regardless of how much stellar light reaches them. At 4.3 light-years from Earth, those moons would represent the closest, potentially habitable environments to the solar system outside of the solar system itself. This is not speculation drawn from optimistic assumptions. It is a logical extrapolation from physical processes that are documented, measured, and understood in the solar system's own gas giant systems. The same gravitational mechanics that sustains Enceladus's ocean would operate on a moon of the Alpha Centauri planet. The same tidal heating that keeps Europa's ocean liquid would function identically at a different stellar distance. The physics does not change because the address changes. The detection of a gas giant at Alpha Centauri A is therefore not merely the detection of one inhospitable world. It is the first evidence that the nearest stellar system, capable of hosting Sun-like star conditions, may also contain orbiting that gas giant in the darkness, beyond any traditional habitable zone worlds with liquid water, worlds where the conditions that origin of life chemistry requires may be met by processes entirely independent of the star's warmth. And that leads to the final question, the one this mystery is truly posing to the whole of human civilization. The story that began in August of 2025 has been told in most public accounts as a story about failure. A planet was found and then lost. A historic announcement was undermined by a non-detection. A discovery unraveled into controversy. The narrative arc, as most people encountered it, moved from triumph to confusion to unresolved ambiguity, a shape that feels in the telling like defeat. That framing is wrong. Not partially wrong, fundamentally wrong, and correcting it requires stepping back from the specific sequence of observations and seeing what that sequence actually represents in the larger context of where science stands at this moment in history. The planet did not fail to exist. The instruments did not fail to function. The researchers did not fail to do their work carefully and honestly. What happened at Alpha Centauri A between May 2025 and January 2026 is that humanity pointed its finest instrument at the nearest sun-like star, operating at the absolute limit of current technological capability, and encountered something that behaved in ways the existing framework of planetary science could not fully account for. That is not failure. That is the precise definition of a frontier. Every field of science has a frontier, a region where the current models run out of explanatory power, where the data exceeds the theory's ability to process it, where observations produce results that the existing vocabulary cannot cleanly describe. The history of science is not a story of steady progress within a stable framework. It is a story of frameworks expanding to accommodate observations that the previous framework could not contain. And the expansion almost always begins with an anomaly, something that should not be happening according to the models that exist at the time, but is happening anyway. The genuinely frightening possibility raised by the Alpha Centauri flickering is not that the planet might be a false positive. If it is a false positive, the scientific process will eventually identify it as one, and the catalogue will be corrected. That is routine. What is not routine, what is actually unprecedented in the modern era of exoplanet science, is the specific pattern of the flickering itself. A source that varies in brightness by factors of 3 or more over periods of hours. At no consistent frequency with no correlation to any known physical mechanism in the bodies involved, does not fit any existing category of astronomical object or phenomenon. It is not behaving like a planet. It is not behaving like a star. It is not behaving like a known category of transient. It is behaving like something that does not yet have a name. Consider what a person living in medieval Europe would have made of a radio signal. Not the concept of radio, the physical phenomenon itself. An invisible oscillation in the electromagnetic field, propagating through space at the speed of light, carrying encoded information across vast distances without any visible medium of transmission. The medieval observer would not have lacked intelligence or curiosity. They would have lacked the conceptual infrastructure to recognize what they were experiencing as a physical phenomenon at all. They possessed no framework within which the observation could be placed, no vocabulary to describe it accurately, no category into which it could be sorted. The experience would be real, the phenomenon would be real, but the observer would be unable to understand it because understanding requires not just data but the theoretical structure within which data becomes meaningful. Pulsars were discovered in 1967 when Jocelyn Bell Burnell detected a radio signal pulsing with such mechanical regularity once every 1.337 seconds that the initial notation in the research log was LGM, standing for Little Green Men. The regularity was so extreme, so unlike anything produced by known natural processes. That artificial origin was briefly considered a serious possibility. Before the physical mechanism, a rapidly rotating neutron star, emitting a beam of radio waves, was identified. The anomaly preceded the understanding by months. The phenomenon existed before the vocabulary for it did. Quasars, when first observed in the early 1960s, appeared to be faint, star-like objects at relatively modest distances, until redshift measurements revealed they were actually among the most energetic objects in the universe, located at cosmological distances and powered by supermassive black holes actively consuming material. The initial observations were real. The initial interpretations were wrong. The corrected interpretation required building an entirely new class of astronomical object that had not existed in the taxonomy before the observations demanded it. Gravitational waves for 99 years occupied a space between theoretical prediction and observational reality that the instruments of each era were simply not capable of bridging. The phenomenon was real throughout. The detection waited for the technology. The flickering of the Alpha Centauri signal may be any of these things. An artifact that better data will eliminate a known phenomenon, operating in an extreme regime that current models have not fully mapped, or something genuinely new. A. behavior of matter and energy in planetary systems that the existing framework does not contain, and that will require a new category to describe. All three possibilities are currently consistent with the available evidence. None of them can be ruled out. Alpha Centauri A is still there, brightening the southern sky every night, over the western deserts, over the Pacific horizon, over the dark places where light pollution has not yet reached, patient and unchanged by the controversy that has swirled around it over the past year. The star itself is indifferent. It does not know it has become the center of the most significant unresolved debate in contemporary planetary science. It does not know that teams of researchers on a planet orbiting a neighboring star have spent months arguing about what is or is not orbiting it. It simply continues fusing hydrogen in its core, warming whatever surrounds it, existing at its 4.3 light-year remove, with the complete serenity of an object operating on stellar timescales. Humanity is watching it now with the best eyes ever. Manufactured mirrors ground to nanometer, precision detectors cooled to temperatures approaching absolute zero, software systems processing more data per observation than was generated by entire decade-long survey programs a generation ago. And the universe, in its characteristic fashion, has responded to this sophisticated attention by maintaining exactly enough ambiguity to prevent a clean conclusion. One signal present, then absent, then flickering. Four hypotheses, each with a fatal flaw. A mystery that grows more textured, not less, with each additional dataset. This is not a story that has reached its end. It is a story that has reached the point where the reader understands what kind of story it is. Not a simple discovery narrative with a triumphant announcement and a clean confirmation, but something rarer and more valuable. A genuine encounter with the unknown, documented in real time, by a civilization that has built instruments powerful enough to see the unknown clearly and honest enough to report what it sees without forcing it into a shape it does not fit. If tomorrow the signal is confirmed, if a new observation resolves the ambiguity and places the planet firmly in the catalogue of confirmed worlds, what is the first thing worth knowing about it? Not its mass, which is already estimated. Not its orbital period, which can be calculated from its position. The first thing worth knowing is whether it has moons. Because if it does, those moons are the next frontier, the next boundary, the next place where the instruments will reach the edge of their maps and find something waiting in the dark that does not yet have a name.